The Earth's magnetic field is very similar to that of a bar magnet, just a lot bigger. View the inside of the Earth here as a bar magnet, and we're going to put the south end up here and the north end down here. Why? Isn't this the North Pole? Well, it is the North Geographic Pole, but let's look at which way the magnetic field lines are going. They're entering at the top, so that means that's the South Pole. That's the South Magnetic Pole. Because if we put a little piece of metal here, or even a little bar magnet, we said that a north pole of a magnet will line up with the field lines. So we'll have a north pole there and a south there. But it's being attracted to this pole, so that must mean this is a south pole, just like we said. So that's kind of cool, that the North Geographic Pole is really the South Magnetic Pole. And vice versa, the South Geographic Pole is really the North Magnetic Pole. What's the origin of this strong magnetic field? Well, it's caused by the circulation of molten iron alloys in the Earth's outer core. We'll talk more about that later. Another little thing here is the magnetic poles are not exactly in the same spot as the geographic pole where the Earth rotates on its axis. It's a little bit off. It's not in the same place. The magnetic field extends from the core of the Earth to the outer limits of the atmosphere, a place called the magnetosphere. This picture over here, here's the sun, here's the Earth, and obviously that's not drawn to scale. The Earth isn't that close. It shows the interaction of the solar wind. This red stuff is the solar wind, and that's comprised of electrons, protons, alpha particles, heavy ions, atomic nuclei, all kinds of stuff that comes out of the fusion reactions within the sun. And the Earth's magnetosphere is this blue thing. The magnetosphere protects life on Earth because without it, all of this ionizing radiation would hit the surface of the Earth, and that would cause great harm, if not basically just wipe out life as we know it. Many of the particles in the solar wind are prevented from entering the Earth's atmosphere by the magnetosphere. And we'll talk later about how moving charges can have a force exerted on them by a magnetic field. That's coming up. So you can kind of see the shielding effect here. The solar wind's not getting through. However, some particles do get through, but what they will do is follow these magnetic field lines down to the north. That would be, let's say, the South Pole, the South Geographic Pole. This would go to the North Geographic Pole where Santa Claus is, because that's where the magnetic field is the strongest. That's where the lines are closer to each other, and it's a much stronger magnetic field. As these particles go through the atmosphere, they'll collide with the oxygen and nitrogen atoms in the atmosphere. They'll excite those atoms, they'll give them a lot of energy. Those atoms will then give the energy back when they go back to their rest state, and that energy will be given off in the form of light. The kinetic energy of all these particles, that energy transforms into light energy, and that's what gives us the aurora borealis and the aurora australis. These are also called the northern lights, and there are many great pictures of them on the web if you'd like to look at them. But this is one I found that actually shows what it looks like in space. Here's the North Pole, right? You've got the Arctic and you got I think that's Greenland. Looks like it should be. Here's Norway, etc. You can see the circle it makes around the magnetic South Pole or the geographic North Pole. These lights are beautiful. You can see them in the higher latitudes. Sometimes they dip down to the northern United States, but if you're up in Alaska or Canada, you can see them. And this is a direct result of the magnetosphere protecting us from the sun's solar wind.